Welcome back to the deep dive. Today, we are doing something that I have been itching to do for a long time. We are stopping the car, popping the hood, and we are looking directly into the engine block of the AI revolution.
It is about time. We spend so much time looking at the paint job, right? The shiny exterior.
Exactly. We look at the output, we say, wow, look, it wrote a sonnet, or look, it generated an image of a cat riding a unicycle on Mars, or I don't know, it passed the bar exam.
Right.
We obsess over what AI does, but we very rarely stop to ask, how is it actually built? Like physically, structurally, what is going on inside those layers of math?
It really is the difference between being a driver and being a mechanic.
Yeah.
And, most people just want to get from point A to point B, and that's fine.
Sure.
But if you really want to understand the vehicle, and I think more importantly, if you want to predict where this technology is going next,
Yeah.
you have to understand the architecture.
And that's what we're doing.
And that is what we are doing today. We're looking at the evolution of deep learning architectures.
And I've got to be honest, looking at the stack of research you brought in, this looks a little intimidating. We have acronyms flying everywhere.
Just a few?
CNNs, RNNs, LSTMs, transformers, JANs, VAEs. It sounds like a very strange, very mathematical alphabet soup. But you promised me there is a narrative here, right? This isn't just a list of technical specs.
Oh, there is absolutely a narrative. It's a story of evolution. It is a story of how engineers and scientists tried to solve very specific problems by baking assumptions into the math.
Okay.
And there's a key term we need to start with before we go anywhere else. If you take one thing away from this whole introduction, it has to be this concept.
Okay, hit me with it.
Inductive bias.
Inductive bias. Okay, let's unpack this immediately because to me, and I think to most people listening, the word bias usually sounds like a bad thing.
It has a negative connotation for sure.
We spend a lot of time talking about how we don't want our AI to be biased, we don't want prejudice, but you're using it in a very different engineering sense, aren't you?
Precisely. In the context of machine learning architecture, bias isn't about prejudice or unfairness. It's about efficiency. It is about the assumptions we bake into the model to help it learn faster.
Oh, an assumption.
Yes. Think of it this way. If I gave you a completely blank sheet of paper, just white space, and I said, draw the universe, what would you do?
I would probably freeze. I'd be paralyzed. Where do I even start? Do I draw a star? A molecule? A person? The possibilities are literally infinite.
Exactly. The search space, as we'd call it, is too big. You wouldn't know where to begin. But what if I gave you a sheet of graph paper and I said, plot the trajectory of this ball over time?
Okay, that's totally different. You've given me a structure. You've given me a grid. I know I need an x-axis for time and a y-axis for height.
Right. I've given you a constraint, and that constraint helps you solve the problem. And inductive bias is simply the model saying, I assume the data is going to look a certain way.
Like a preconceived notion for the data.
Exactly.
Yeah.
For example, if we are building a model to look at images, we might bake in the assumption that the data has a spatial structure, that pixels next to each other are related.
Right.
If we look at language, we assume it has a timeline. That order matters.
So it's like giving the AI a head start. Instead of letting it figure out the laws of physics from scratch, we say, hey, heads up, gravity exists, and time moves forward.
That's the perfect way to put it. It's a trade-off.
Yeah.
The more assumptions or bias you give the model, the faster it can learn with less data, but the more rigid it is.
And if your assumptions are wrong...
If your assumptions are wrong, the model fails spectacularly. And the history of deep learning is really the history of changing those assumptions, of finding better and better biases.
And looking at this timeline we're about to walk through, it seems like we started with very heavy assumptions, very strong inductive biases, and as we have moved toward the modern era of generative AI, we have actually started removing them.
That is the fascinating arc of this whole story. We are going from rigid structure to massive data. We are starting to trust the data more and the pre-baked structure less.
That is a fascinating trajectory. Okay, let's walk down this timeline. We have 4 main stops on this roadmap.
4 big eras.
We've got the eyes, the visual specialists, we've got the memory, the sequential storytellers, we've got the brain, the transformers, and finally, the creators, the generative models.
That is the plan. And it all starts with vision. How to make a machine see.
Part 1, the visual specialists. Convolutional neural networks, or CNNs, these are the models that learn to see, right?
Right.
This is the technology behind facial recognition, self-driving cars spotting stop signs, medical imaging detecting tumors. This is the bedrock of computer vision.
That's right. And to understand CNNs, you really have to go back to basics and understand the nature of an image. If you strip away all the artistry, what is a digital image, really?
Well, at the most basic level, it's just a grid. It's a spreadsheet of numbers, right? Pixel values for red, green, and blue.
Correct. It is grid-like data, and because it is a grid, it has a very specific property that we can exploit. It's called spatial locality. And this is the first major inductive bias we are going to talk about.
Spatial locality. It sounds fancy, but I'm guessing the concept is actually pretty simple.
It is. It simply means that pixels that are close to each other on that grid are more likely to be related than pixels that are far apart.
Okay, let me try to ground that. If I see a pixel that is, say, a patch of skin tone, the pixel right next to it is probably also skin tone.
Exactly.
They are part of the same nose or the same cheek or whatever.
Right. If you are trying to identify a face, finding a nose helps you find the mouth because they are structurally close together. You don't need to cross-reference a pixel on the nose with a pixel way up in the sky in the background to figure out it's a face. The local neighborhood matters most.
So before CNNs, how did computers even try to look at images? What was the naive approach?
The naive approach was something we call a fully connected network, or a multi-layer perceptron. Imagine taking that grid of pixels, say a 4K image with millions of pixels, and flattening it.
Flattening it, like a steamroller.
Sort of. You just unroll it into one single long line of numbers. And then you connect every single one of those pixels to every single neuron in the next layer of the network.
Wait, so the pixel in the top left corner is connected to the same neurons that are looking at the bottom right corner.
Everything is connected to everything. It treated the image as if the order of pixels didn't matter at all. It completely ignored the spatial structure we just talked about.
That sounds incredibly inefficient. If I have a 4K image, that's millions and millions of pixels connecting everything to everything. My God, that's billions of connections, billions of parameters to learn.
It's computationally impossible for large images, and it's wasteful. You're asking the computer to learn relationships that don't exist, like the relationship between a blade of grass on the left and a cloud on the right. CNNs fix this by respecting spatial locality. They don't look at the whole image at once, at least not initially. They look at small, local patches.
And this leads us to the second key concept for CNNs. You called it the moving cat problem.
Right, the fancy term is translation equivariance, which sounds incredibly complex, but the example is super simple.
Let's hear it.
Imagine you have a picture of a cat. In one photo, the cat is sitting in the bottom left corner. In another photo, the exact same cat has walked over to the top right corner. It is the same cat.
Right. To me, a human, it's obviously just a cat that moved. The catness is the same.
But to a computer seeing a grid of numbers, those are completely different inputs. The cat pixels have shifted coordinates. A fully connected network would have to learn cat in corner A as a completely separate concept from cat in corner B.
It would have to memorize the cat twice.
Or 100 times that the cat could be in 100 different places. It lacks the ability to generalize.
That seems really tedious. We want the AI to understand that a cat is a cat, regardless of where it is on the screen.
Exactly. Translation equivariance means that if the object shifts or translates across the image, the network's internal representation of it shifts with it. But the final classification remains the same. The network says, aha, I see the cat pattern here. And then later, I see the cat pattern there. It's the same pattern.
So how does the CNN actually do that? How does it spot the cat regardless of where it is without memorizing every single possible location?
It uses a brilliant mechanism called weight sharing. This is the secret sauce of the CNN.
Weight sharing.
Instead of a massive web of connections where every neuron is different, imagine a small flashlight.
A flashlight. Okay, I'm visualizing it. A little beam of light.
This flashlight is actually a small filter, a little grid of numbers, maybe 3 pixels by 3 pixels or 5 by 5. We call it a kernel. And we slide this flashlight, this kernel, across the entire image, row by row, column by column. At every single spot, we perform a mathematical operation called a convolution.
And that convolution just checks if the pixels under the flashlight match the pattern of the filter.
That's a great intuition. If the filter is a pattern for a vertical line, the convolution will have a high value when the flashlight is over a vertical line in the image.
So we are using the same flashlight, the same filter with the same numbers in it, to scan the whole image.
Yes, that is the sharing in weight sharing. We are sharing the weights of that filter across the entire image. If that filter is designed to detect a vertical edge, like the side of a building or the pupil of a cat's eye,
Hmm.
it will find that vertical edge, whether it's in the top corner or the bottom corner.
Because it's the same detector.
We reuse the same eye across the whole visual field.
That drastically cuts down the work the computer has to do. Instead of learning a million different parameters for a million locations, you just learn the parameters for that one little filter, and then you just apply it everywhere.
Precisely. It reduces the parameter count by orders of magnitude. It makes the learning efficient. It allows us to stack these layers. The first layer finds simple things, like edges. The next layer takes those edges and combines them into shapes, circles, squares.
And the next layer combines shapes into features: eyes, noses, tires, doorknobs.
And you keep building that hierarchy until eventually a layer of the top says, I see an eye, a nose, two pointy ears, and some whiskers. That's a cat.
But there was a limit, right? I saw this in the notes. For a long time, historically, we couldn't make these networks very deep. Before 2015, if you tried to build a CNN that was deeper than, say, 20 or 30 layers, it just wouldn't learn. It would actually get worse. It would stall out. Why?
This is the infamous vanishing gradient problem.
Mm.
And to understand this, we have to touch on the math of how these things actually learn. They learn via a process called backpropagation.
Which is basically the network checking its work, right? It makes a guess like, I think that's a dog. It checks the answer, sees it was a cat and it was wrong.
Yeah.
And then it sends the error signal backwards through the network to update all the settings.
That's a perfect description. It sends that error signal, that gradient, back using the chain rule from calculus. Now, you don't need to know the calculus, but you need to know this one key fact. The chain rule involves multiplying a series of numbers together to calculate the adjustment for each layer.
Okay.
Now, imagine those numbers, which represent the derivatives of the activation functions, are small, almost always less than 1.
Okay, basic math here. If I take 0.5 and multiply it by 0.5, I get 0.25. If I do it again, I get 0.125. The number gets smaller and smaller very, very fast.
Exactly. It decays exponentially. So as that error signal travels back from the final layer, layer 50, to layer 49, to layer 48, by the time it gets all the way back to layer 1, the signal is basically 0.
The signal has died.
It has vanished. The early layers, the ones that are supposed to detect the most fundamental things like edges and curves, never get the memo that they need to change. They stop learning.
So the network has a brain, but the optic nerve can't talk to the visual cortex. It's a communication breakdown.
A total breakdown. For years, this was the wall. You just couldn't train very deep networks. And then comes 2015, the breakthrough, ResNet.
Visual networks.
This is a pivotal moment in AI history. It sounds technical, but the solution was just beautifully simple. ResNet introduced the skip connection.
I love this concept. It's like an express lane or an HOV lane on a highway.
That is a perfect analogy.
Yeah.
In a standard network, the data has to go through every single layer, getting processed and transformed and squashed at every step. It's like being stuck in local traffic.
Bumper to bumper.
In ResNet, we add a parallel path. We say, go through the processing layer, BOT. Also, let's take a copy of the original data from before the layer and just add it directly to the output after the layer.
So mathematically, instead of just calculating some function x to x, we are calculating next to x plus x res. We are adding the original signal back in. We are preserving it.
Yes. And think about what that does for the gradient, that error signal we talked about that's traveling backwards. During backpropagation, that plus x path acts as an information superhighway. The gradient doesn't have to squeeze through all the complex transformations where it might get multiplied by tiny numbers. It can flow straight back along the skip connection, unchanged. The derivative of 6-baller's line is just 1.
So the signal doesn't vanish. It can bypass all the traffic jams. It can get from layer 50 to layer 1 with its strength intact.
And the result was explosive.
Yeah.
We went from struggling to train 20 layers to easily training 100 layers, or 152 layers, or even 1,000 layers. ResNet allowed us to bathe the incredibly deep, powerful visual models we see today. It didn't just inch the field forward, it was a quantum leap. It solved the depth problem.
So that's the visual side. We conquered the grid. We mastered the static image by using the inductive bias of spatial locality and then solved the depth issue with ResNet. But the world isn't just static images.
Far from it.
The world happens in time. We speak in sentences, stock markets move in trends, music has a rhythm. It's all sequential.
And that brings us to part 2, the sequential storytellers. Recurrent neural networks, or RNNs, and their much more capable children, LSTMs.
This feels like a totally different beast. With images, you can kind of see the whole picture at once. But with language, you can't understand the end of the sentence until you've read the beginning. The order is everything.
Right. This is a shift to sequential data. The inductive bias here is temporal.
Mm.
The assumption is that order matters.
Hmm.
Dog bites man is a very, very different piece of information from man bites dog.
Same words, totally different meaning.
The words are the same, the structure is similar, but the sequence defines the meaning.
So how did the classic vanilla RNN handle this?
It processed data step by step, which is very intuitive. Imagine reading a book through a tiny slit in a piece of paper where you can only see one word at a time.
Okay.
You read a word, you update your mental state about what's happening, then you slide the paper over to the next word. The RNN has a hidden state, a sort of memory, that it updates at each step and carries forward from step T along to step 2
This is
all.
a loop. The output from one step becomes an input to the next step.
Exactly. It's a feedback loop that allows it to maintain a memory of what came before.
But there's a problem with that, isn't there? I mean, just intuitively, reading word by word sounds slow.
It is incredibly slow, especially for computers. We call this the sequential bottleneck. Modern hardware, like GPU's graphics processing units, they are built for parallel processing. They love to do a million things at once. They're like a highway with 1,000 lanes.
But an RNN is like a single-lane dirt road. You can only go one car at a time.
That's a perfect description. With an RNN, you are forced to wait. You cannot calculate the hidden state for the 10th word until you have completely finished the calculation for the 9th word. You can't do the 9th until you finish the 8th. It kills hardware efficiency. You have this massive supercomputer, and it's sitting there twiddling his thumbs, waiting for the previous step to finish.
So it's slow. And did they have the same vanishing gradient problem as the CNNs?
O is even worse, much worse. In a deep CNN, different layers have different weight matrices.
Yeah.
In an RNN, because of that loop, you are reusing the same weight matrix at every single time step.
The same one.
You are multiplying by the exact same matrix over and over and over again, hundreds of times for a long paragraph.
So if the eigenvalues of that matrix are less than 1,
The memory vanishes. The gradient goes to 0. The network completely forgets what happened at the beginning of the sentence by the time it reaches the end.
it creates a model with severe short-term memory loss.
Exactly. It might start a sentence talking about the keys to the cabinet. And by the time it gets to the verb at the end of the sentence, it's forgotten what the subject was. It forgets if it was plural or singular. It might say, is on the table instead of are on the table.
And what if the eigenvalues are greater than 1? I assume that's bad too.
Then you get the opposite problem, exploding gradients. The numbers get so huge they overflow the computer's memory. The values turn into nan, not a number. The whole training process just crashes.
Wow. So it was a nightmare. You had networks with amnesia or networks that would have a mathematical seizure. Not a great choice.
It was a very, very narrow tightrope to walk, which is why, for a long time, RNNs were useful for short sequences, but fell apart on anything longer.
Enter the solution, the LSTM, long short-term memory, which frankly is a bit of a clunky name, but it changed everything for natural language processing for a long, long time.
LSTMs were brilliant. They were designed specifically to solve that vanishing and exploding gradient problem. They introduced a much more complex internal structure to handle memory more intelligently. The core innovation was the cell state.
The notes describe this as a conveyor belt. I like that.
Yes. Imagine a separate conveyor belt running straight through the entire sequence, right alongside the main processing line. Information can be placed on this belt and can flow down the chain with very, very minor interactions. It's a protected channel. It preserves the long-term signal.
But we have to interact with it somehow. We can't just let information from the start of the book run forever without changing it. We need to update memories, add new things, forget old things.
Exactly. And we control the conveyor belt using gates. Think of them as controllable valves or checkpoints along the belt.
Valves. Okay.
The LSTM has 3 key gates that learn what to do. First, there's the forget gate.
That sounds harsh. Forget gate. Why do we want the network to forget?
It's absolutely essential. Think about reading a book. If you finish a chapter about Bob's life in London and start a new chapter about Alice's childhood in Tokyo, you need to forget the context of Bob in London to make mental space for Alice in Tokyo. You need to clear out the stale context.
Okay, that makes perfect sense. So the forget gate looks at the new word and the old memory and decides, okay, this info is stale, let's dump it.
Right. It's a sigmoid layer, a math function that outputs a number between 0 and 1 for each piece of information in the cell state. 0 means completely get rid of this. 1 means keep it perfectly.
Okay, so we clear the trash. Then what?
Then you have the input gate. This gate decides what new information from the current step is worth saving. It looks at the new word and says, okay, this seems important, let's update the memory. It decides what new stuff to add to the conveyor belt.
And the third gate.
The output gate. This decides what part of the conveyor belt memory is relevant for the very next step. It decides what to reveal to the rest of the network to make the next prediction.
The technical key here, and correct me if I'm wrong because this seems important, is how it updates that conveyor belt. In the old RNNs, it was all multiplication, which caused the vanishing signal. In LSTMs, the update to the cell state is additive.
Bingo. That is the magic.
Hmm.
The core update equation is essentially CTT versus old stuff, plus text new stuff. Because we are adding information rather than just repeatedly multiplying it, the gradient doesn't vanish nearly as easily.
The addition creates that ResNet-style superhighway for the gradient.
It's the exact same principle. It allows the signal to ride that conveyor belt all the way back to the beginning of a long sequence. It gave AI a functional long-term memory.
LSTMs were the kings of language for years. I remember when Google Translate switched to them, it got noticeably better overnight. It stopped producing just word salad and started producing coherent, readable sentences.
It was a massive leap.
But they were still slow. They still had that fundamental sequential bottleneck. You still had to process word by word, step by step. You couldn't parallelize it.
And that limitation, that slowness, was the Achilles heel that set the stage for the next revolution, the moment where we just abandoned recurrence entirely.
Part 3, the transformer revolution. This is the big one. This is the architecture behind ChatGPT, Claude, Gemini. Basically, the entire generative AI boom we're living through right now is built on this foundation.
The paper that introduced this architecture in 2017 was famously titled, "Attention is All You Need." And it was such a bold claim. They were basically saying, forget the conveyor belt, forget the step-by-step processing. We don't need recurrence. We just need this one mechanism. Attention.
So what replaced the step-by-step process? If I'm not reading left to right anymore, how am I reading?
You are looking at everything at once. The transformer takes the entire sentence or the entire paragraph or the entire document and processes it all simultaneously. It looks at global dependencies.
Global dependencies.
Right.
So the first word in a paragraph can look directly at the last word in the paragraph.
Yes, instantly. In an LSTM, for the first word to send a message to the last word, it had to pass that message through a chain of, say, 500 intermediaries. It's like a game of telephone. By the end, the message is distorted or lost.
Right.
In a transformer, the distance between any two words is 1. They're all connected directly.
That sounds incredibly powerful, but also incredibly expensive.
Yeah.
If everything is looking at everything, isn't that a lot of connections to calculate?
It is. The complexity is quadratic, or Howard's 2. That means if you double the length of the text, the amount of computational work quadruples. It gets very expensive very fast.
But the trade-off is worth it.
The trade-off is worth it because it's perfectly parallelizable. GPUs love it. Because we aren't waiting for step 1 to finish before we start step 2, we can fire all the cannons at once. We can throw massive hardware at the problem, and it scales beautifully.
Let's dig into the mechanism itself. Self-attention. The notes have this trio of terms that always comes up. Query, key, and value. QKV. This is usually where people's eyes glaze over. I need a really good analogy.
Okay, let's go with a library or a filing system. It's a classic one for a reason. Imagine you are doing research for a paper. You have a specific topic you want to know about. That is your query.
Okay, my query is, what was the impact of the printing press?
Perfect. That's your query. Now, you walk into the library. There are thousands of books on the shelves. Each book has a title or a label on its spine. That label is the key.
So the key is the label I'm matching against. History of Rome, quantum physics, the Renaissance.
Exactly. You compare your query, printing press, against all the keys on the bookshelf. You look at History of Rome, low match. You look at quantum physics, 0 match. You look at the Renaissance or History of Communication, high match.
And that match is a score.
Mathematically, it's a dot product. It gives you a score of how relevant that book is to your question.
So I find the books with the highest scores. Then what?
Then you take those books off the shelf and you open them up to get the actual content inside. That content, the text in the book, is the value. You pull the information from the most relevant sources.
Query, key, value. I ask a question, I check the labels for relevance, I extract the information from the most relevant items. That makes sense.
Now here's the wild part. In a transformer, every single word in the input text creates its own query, key, and value.
Every word.
Every single. Let's take a simple sentence. The bank of the river was muddy. The word bank needs to figure out what it means. Is it a financial institution or the side of a river?
Right, context is key.
So the word bank sends out a query. The query is essentially, what kind of context am I in? What am
And
I?
it checks the other words in the
It
sentence.
checks its query against the keys of all the other words. It looks at the key for the, low relevance. It looks at the key for river. The word river holds up a key that basically screams water context, geography context. That's a high match score.
So bank pays a lot of attention to river.
Exactly. It then pulls the value from river. It absorbs the watery context from that word. And as a result, its own representation gets updated. It becomes river bank, not financial bank.
And this is happening for every single word all at the same time. Muddy is looking at river, river is looking at bank.
It is a massive parallel context mixing machine, a symphony of words all talking to each other at once to figure out their collective meaning.
Now, there is a specific math detail here that the expert notes highlighted, and it seems important, the scaling factor. The formula is scaled dot product attention. We divide the result of that matching process by the square root of the dimension of the keys. Why? Why do we need to shrink the numbers?
This is a really subtle but absolutely crucial piece of engineering. It goes back to the gradients, just like with CNNs. When we do that dot product between the query and the key, if the vectors are large, and in modern AI they are huge, maybe thousands of dimensions, that dot product can result in a really, really large number.
Okay, we get a big number, so what's the problem?
The problem is the next step. We feed that big number into a softmax function. Softmax is what turns all the raw relevance scores into a nice probability distribution that adds up to 1. But here's the catch. If the input numbers to softmax are too large, softmax saturates.
Saturates, like a wet sponge that can't hold any more water.
It's a great analogy. Think of it like a light dimmer switch. Softmax takes a range of numbers and squishes them. If the numbers are huge, it pushes them all the way to the extreme edges of its range 0 or 1. It becomes a hard on-off switch instead of a smooth dimmer.
And when you are at the extreme edge of a curve,
The gradient is 0, the slope is flat, the model stops learning. You try to tell the switch to adjust, but it's stuck at the maximum. By scaling the numbers down, by dividing by that square root, we keep the values in the sweet spot of the softmax curve, where the gradients are nice and juicy and flowable. It keeps the dimmer switch adjustable.
that is a critical piece of engineering. It literally keeps the math from breaking down and the learning from stopping.
It's one of those little details that made the whole thing work at scale.
Speaking of making things work at scale, transformers are heavy, they are big, running them is not easy. The notes mention flash attention. I keep hearing this term thrown around. What is it, and why was it so important?
Flash attention is a brilliant hardware-aware optimization. It doesn't change the math of attention, it changes how the math is executed on the GPU. It solves a memory bottleneck.
A memory problem.
You see, GPUs have two main types of memory. They have HBM high bandwidth memory, which is huge, but relatively speaking, slow. Think of it as your giant pantry in the basement. It holds a lot of stuff, but it's a long walk to get anything.
Okay, and the other kind?
And they have SRAM static RAM, which is tiny but incredibly fast. This is your kitchen counter. You can access anything on it instantly.
Okay, pantry versus counter, I can work with that.
The standard attention calculation creates a massive intermediate matrix, that $1 Nile grid of scores we talked about. For long text, this matrix is way too big to fit on the kitchen counter, SRAM.
So you have to use the pantry.
You have to. So the GPU is constantly walking to the pantry, HBM, getting a few numbers, bringing them to the counter, doing a tiny bit of math, writing the result back to the pantry and repeating that over and over and over.
Lots of walking back and forth. The actual cooking is fast, but the prep time is killing you.
Tremendous waste of time. The bottleneck isn't the math, it's the memory access. Flash attention uses a technique called piling. It's clever. It breaks the big attention matrix into small blocks or tiles that can fit entirely on the kitchen counter.
Ah,
It grabs one block of ingredients from the pantry once, brings them to the counter, does all the math for that block right there in superfast SRAM, and only goes back to the pantry when it's completely finished with that block and ready for the next one.
it effectively organizes the cooking so you aren't running around the kitchen like a maniac.
Exactly. It is I/O aware. It minimizes those slow read-write operations to HBM. This made training and running these massive models significantly faster and cheaper. It's one of the key reasons we can now have context windows of 100,000 tokens or even 1,000,000 tokens.
There is one more optimization mention here, KV caching. This is specifically for when the model is generating text, right? Like when I'm watching ChatGPT type out an answer word by word.
Yes, this is a huge one. but only for inference, not for training. Imagine you've asked the model a question, and it has generated 100 words of an answer. It's now about to generate word number 101.
Okay.
To generate word 101, the transformer needs to attend to all 100 previous words. It needs their keys and their values to understand the context of what it has already said.
Right, of course.
Without caching, for every single new word, you would have to recalculate the keys and values for all 100 previous words from scratch. It's like rereading the entire book from page 1 every single time you want to say the next syllable.
That sounds exhausting and incredibly wasteful.
It is. So we use KV caching. As we generate each word, we save its key and value in the GPU's memory. We cache them. So when we go to generate word 101, we just pull the pre-computed keys and values for the first 100 words from the cache and only do the fresh computation for the new word.
That makes so much more sense. But there is a trade-off, I assume.
VRAM, video RAM, it eats up memory like crazy. The longer your conversation, the bigger the cache gets. That is why running long context requires these huge, expensive GPUs with tons of VRAM. You are trading memory space to save a massive amount of compute time.
Okay, wow. We have covered the architecture of understanding. We have the I, the CNN, the memory, the LSTM, and now the brain, the transformer. But now we are moving to the final frontier, which is really what everyone is excited about today, the creator's generative models.
This is part 4. And this is where the paradigm shifts again. Up until now, we have mostly talked about models that classify or process data. Is this a cat? What is the sentiment of this sentence? Now we are asking the model to create new data, to learn the underlying probability distribution of the world, and then sample from it to make something new that has never existed before.
And we start with the rebels of the group, the ones that sound like a street fight, GDANs, generative adversarial networks.
I love GANs. The concept is just so elegant and so cinematic. It is a game. A zero-sum minimax game. You have two neural networks that are locked in a battle fighting each other.
The forger and the detective, that's the classic analogy.
Exactly. You have the generator. Its job is to be an art forger. It takes random noise as input and tries to create fake data, fake images of faces, for example. Then you have the discriminator. Its job is to be the art detective. It looks at an image and has to say, this is a real one from the training set, or this is a fake produced by the forger.
So they train together in this adversarial loop. The forger gets better at forging because the detective gets better at spotting fakes. And the detective gets better because the forger is constantly inventing new tricks. They push each other to perfection. Ideally.
Ideally. But in practice, GANs are notoriously unstable. They're incredibly difficult to train. One of the biggest problems is a failure mode called mode collapse.
Mode collapse. That sounds dramatic. What is that?
Imagine the forger, the generator, discovers a loophole. It realizes that the detective is really bad at spotting fake images of, say, golden retrievers. Maybe the detective just has a blind spot and assumes all golden retrievers are real. So what does the forger do?
It stops trying to paint poodles or bulldogs or anything else. It just paints golden retrievers all day, every day, because it's an easy win.
Exactly. It exploits the loophole. It finds one mode of the data distribution that it can produce perfectly to fool the discriminator, and it just produces that over and over again. You lose all diversity. You wanted a model that could generate all kinds of dogs, but you only got one. The generator collapses onto a single mode.
So how do we fix that? The notes mention something called WGN.
Wasserstein-Jan. This was a big improvement. It changes the fundamental math of how we measure the distance between the distribution of real images and the distribution of fake images. Standard GANs use something called JS divergence, which has some mathematical problems.
Right.
WGN instead uses the Earth mover's distance.
Earth mover's distance. That sounds like a term from a construction site.
The intuition is exactly that. Imagine the probability distributions are two different piles of dirt. The Earth mover's distance asks, what is the minimum amount of work, which is mass times distance, that I have to do to move the dirt from the fake pile and rearrange it so that it perfectly matches the shape of the real pile?
Okay, I can visualize that. Why is that measurement better than just checking for overlap, which is what the old method did?
Because it provides a smooth, meaningful gradient, even when the two piles of dirt don't overlap at all. The old method would just say, 0 overlap, you're wrong. WGN says, you are wrong by this much, and you need to move the dirt in this direction to get closer. It gives the generator useful feedback, even when it's very far from the correct answer. It allows the model to learn its way out of the hole instead of just getting stuck.
Okay, so GANs are the fighters. Next on our list, we have the VAEs, variational autoencoders. These seem a bit more, I don't know, civilized, more mathematical.
They are definitely more mathematically grounded. The goal of a VAE is to learn a compressed representation of the data. It's an encoder-decoder architecture. The encoder takes a messy, high-dimensional input, like a 256 by 256 image, and compresses it down into a smooth, continuous, latent space.
Latent space. We hear this term all the time now. It's like a compressed map of concepts, right? Where similar things are close together.
Exactly. All the happy faces are in one corner of this map, all of the sad faces are in another. It's a low-dimensional cloud of data points. Then, the decoder part of the VAE can take a set of coordinates from this cloud and reconstruct the original high-resolution image.
But there is a crucial twist. It doesn't just map an image to a single point in the cloud. It maps it to a distribution, a little probability cloud of its own.
Correct. And this is key. The loss function, the thing we were trying to get the VAE to minimize during training, is called the ELBO, or the evidence lower bound. It has two warring terms.
Warring terms again. Seems to be a theme in AI. What are they?
Term one is the reconstruction loss. Does the output image look like the input image? It wants perfect pixel for pixel accuracy. Term two is the KL divergence. This is the regularizer. It basically says, I don't care what the data looks like, you must force the entire structure of this latent cloud to look like a standard Gaussian distribution, a nice neat bell curve centered at 0.
Why do we care if the cloud looks like a bell curve? Why not just let it look like whatever it wants to as long as the reconstruction is good?
Because we want the space to be generative. We want it to be dense and navigable. If we didn't have that second term, the model might just memorize specific points for each training image and leave huge empty gaps in between them.
And if you try to sample from a gap, you get nonsense.
You get garbage.
Yeah.
By forcing everything into a standard bell curve shape, we ensure that the space is smooth. If we pick a point on the map that is halfway between a happy face and a sad face, we get a valid neutral face, not just static noise. It allows us to interpolate and morph between concepts.
There is a famous trick here too, the reparameterization trick, which is a mouthful. What problem does that solve?
Yes. This is a very clever bit of engineering.
Uh,
In a VAE, you have a step where you have to sample from that random distribution we just talked about. You have to pick a random point from the little cloud.
and randomness is a problem for backpropagation, for calculating gradients.
A huge problem.
Yeah.
You cannot calculate the gradient of a random coin flip. You can't ask the question, how would the final output change if the random number had been slightly different? Because it was random. It's not a deterministic function. It breaks the chain rule. The gradient hits a brick wall.
So how do we get around that? How do we backpropagate through randomness?
We cheat.
Hmm.
We move the randomness to the side. Instead of the network node being a random number generator, we say the node is deterministic. The network learns two deterministic things: the mean and the standard deviation of the little cloud.
Okay, so those are just regular numbers.
They are. Then we take the randomness, a number, epsilon, sampled from a simple fixed noise source, and we inject it as an input from the outside. The final latent variable is calculated as 0 plus sigma epsilon 2.
So the network structure itself is just solid pipes, and we're just pouring a little random sauce into the top of the funnel.
That's a perfect way to put it. This allows the gradient to flow backwards through the pipes, through Mu and Enseguida, so the network can learn how to shape the cloud while still keeping the stochastic random nature we need for it to be a VAE. It's a brilliant workaround.
Finally, we reach the current state of the art, the technology that really took over the world, the models behind DLE, Midjourney, and especially Stable Diffusion. Diffusion models.
This is the most fascinating one to me because the core idea is so beautifully counterintuitive. It starts by systematically destroying data.
The forward process.
Yes. You take a perfectly good image, say a high-resolution picture of a dog, and you slowly, step by step, add a tiny bit of Gaussian noise to it. You add a little static, then a little more in the next step, then a little more, until eventually, after 1,000 steps, the image is just pure static, random snow. You've completely destroyed all the information.
You take a masterpiece and you turn it into television static.
Bro.
Why on earth would you do that?
Because you record exactly how you ruin it at every step. Then the reverse process is training a neural network, usually a type of CNN called a UNet, to do the opposite. You show it one of the noisy versions and you ask it, hey, what was the noise that was added to the previous step to get to this step?
And if it can accurately predict the noise.
It can subtract it. It learns to denoise the image one step at a time. It learns to reverse entropy. So to generate a new image, you just start with a fresh patch of pure random noise and you run the model backwards. Step by step, it subtracts the noise it thinks should be there, and an image slowly emerges from the chaos.
It's like a sculptor staring at a block of marble, but the marble is pure static, and the chisel is a mathematical noise predictor.
That is a very poetic and accurate way to put it. And because it has seen billions of images during training, when you give it a text prompt, like a photo of a dog, it uses that information to guide the denoising process toward the dog region of the vast probability distribution it has learned.
But doing this pixel by pixel must be incredibly slow, right? A 1024 by 1024 image has over 1 million pixels. Denoising 1 million pixels for 50 steps, that's a heavy, heavy compute load.
Extremely slow, and that is why the original diffusion models were very academic and not very practical. The game changer was latent diffusion, LDM. This is the key insight behind stable diffusion.
It combines the VAE we just talked about with the diffusion model.
Yes, it's the best of both worlds approach. Instead of doing that slow, expensive diffusion process on the massive grid of pixels, it first uses the encoder from a pre-trained VAE to compress the image into that small, compact, latent space.
The concept cloud, the map of ideas.
Right. It might compress the image by a factor of 64. So now you have a much smaller grid to work with. Then it does the entire diffusion process, the noise adding and the iterative removing inside that compressed, low-dimensional latent space.
So is working on the concepts, on the ideas, not on the raw pixels.
It is so much faster, so much more efficient. And at the very, very end, once it has a clean, latent representation, it uses the VAE's decoder one time to turn that latent concept back into a beautiful high-resolution image.
What a journey. I mean, we went from the rigid grid-based logic of CNNs to the sequential memory of LSTMs to the massive parallel attention of transformers, and finally to this chaos-reversing magic of diffusion models working in a latent space.
And if you look at the arc, look at what has been happening to that idea we started with, inductive bias.
Tell me. Summarize the narrative for us. Where have we gone?
In CNNs, we had a very strong, hard-coded bias. Spatial locality matters. Pixels near each other are special. In LSTMs and RNNs, we had a strong bias. Sequence and order matter above all. In transformers, we weakened that bias significantly. We said everything can look at everything. Let the data itself figure out what's important via attention.
We started removing the architectural training wheels.
We did. And in diffusion, we've taken that even further. We are literally starting with noise-pure, unstructured randomness. And we are forcing the model to learn the entire structure of the world from scratch.
We are trusting the data and the scale of the model to find the patterns, rather than telling it what patterns to look for.
We are. As we get more compute and more data, we find we need fewer and fewer baked-in assumptions. We can let the model find patterns that are far too complex or subtle for us to hard-code as engineers. We are moving from feature engineering to architecture engineering to now simply scale.
That is a powerful thought. We are building machines that don't just follow our rules about the world, but discover rules we didn't even know existed.
And that leads to the final provocation for today. Think about the reparameterization trick and the core idea of diffusion models. In both cases, we are taking randomness noise, chaos, epsilon dollar, and we are filtering it through a learned structure to create meaning and order.
We are turning noise into signal.
Isn't that, at a fundamental level, what intelligence is? Taking the chaotic, high-entropy sensory input of the universe and finding the order, the patterns, the structure within it. We are literally building machines that reverse engineer order from chaos.
I am definitely going to be thinking about that one for a while. Next time you see an AI-generated image, just remember, it started as pure static, and it found its way home through a latent space. Thank you for joining us on this deep dive.
It was a pleasure.
We'll see you next time.